So I'm going just to make a review of that. So the first lecture will be again a bit standard for the people who have already taken a class in general relativity. And then there will be a second lecture, the one after, which is about cosmological perturbations. So that is a bit heavier. I have all the notes here that you will have. So you don't have to take notes. It's a bit heavy in terms of calculations. But all the calculations are done here, so you will have all the details. So it's mostly about understanding the logic. And then after that, in the afternoon, we will go with Mathematica and see a bit what to do with it. And finally, tomorrow, we will start really modify gravity with what is called FOFA gravity and the chameleon mechanism. So that will be tomorrow. So today, we continue a bit standard on the test of general relativity. And there are many tests actually which have been done since 1915, the publication by Einstein of the paper. And the first test, which is the most famous one, is the perihelion advance of Mercury. Okay, so this is a very famous experiment and it's easy to do the calculations. In this context, you will find it in most of the textbooks. What it says is the following, is that you have a two-body problem. So you have the Sun and you have the Earth. So you have a two-body problem and we know how to solve that in classical mechanics, and we know that actually the trajectory will be elliptical. So this is the Kepler's law. So we know that we will have a motion like that, and this is Kepler. Okay, so this we know very well how to solve that. The point is, in the solar system, we don't have only two bodies, but there are many other planets. So the other planets, what they do is that they produce a perturbation of this two-body problem. The two-body problem is simple, but we have perturbations. So what is the consequence? The consequence is that we have the Sun, and we have the motion of the Earth, and the motion of the Earth will be a bit shifted every time. So every time it will be a bit shifted like this. So we'll have a motion like that, that the trajectory is not an ellipse anymore, but it gets shifted all the time a bit by some angle. So here I exaggerated a bit the angle, but this comes only because of the other objects. You have plenty of other objects in the solar system, and each one produces a perturbation. So each one is producing a change in the elliptical orbit. So this we can calculate it, and people did these calculations. And the closest point to the Sun, so if we take this closest point when we are very close to the Sun is called the perihelion. So this is the closest point to the Sun. So what we are looking is how this closest point to the Sun actually is shifting actually. So first it was here, then it goes here, then it goes here, etc. So this perihelion gets actually shifted a bit, so you get a rotation of it. So this comes just by the perturbation of the other planets. Just for the vocabulary, this is called the aphelion. This is the point where we are very far from the Sun. So people did these calculations, and they were pretty good in the 19th century in these very tough calculations, because you have to take into account each body you take into account perturbatively. And people, they found that there is a shift, and you get, mostly it's Le Verrier who did this final work. So Le Verrier did these perturbations, and he found that you get 526.7 seconds of arc per century. So of course, during 1 year, you don't have a big angle So you have to look at it during a long time. You wait 100 years, so 1 century, and then you get an angle that you can observe, which is that. So this is the accumulated shift during 1 century. So this is just the classical effect, which comes from the other planets. So people, they try that is the work by Leverrier. There is another person just after, Newcomb, who tried to be a bit more precise on the perturbations. He went a bit further, and he found actually that it's 531 seconds of arc. So it was a bit more precise. The only problem is that what you observe is not that. So what you observe is 574 seconds of arc per century. So there is a problem between the theory and the observation. We observe that actually there is this shift, for sure. You observe it in the sky. And the problem is that it's much larger than what you calculate from the theory of perturbations. And there is a bit of difference. What is the difference? It's 43. So this is actually what is missing. So something doesn't work here, that you use all the theory of perturbations, and at the end actually you have something is missing, and this is this 43 seconds of arc. So there was different theories. One of them was to say that there is another planet actually, because you take into account all the planets, Venus, the Earth, etc. All these planets, they are producing some effect on this shift, but you can say, okay, maybe there are some planets that we don't know. So maybe there is some planet which is producing this effect, and this is the work by Leverrier, the first one, who said the following, is that there is an additional planet. So here there is the Sun, there is Mercury, which is for us the first planet, but he said that there is another planet here, and this planet is producing a perturbation on the motion of Mercury. So he did all the calculations. What is the orbit of this planet? What is the mass of this planet, etc., in order to produce exactly 43 seconds of arc. And this planet, he called it Vulcan. So that was the name he gave to the planet. So the planet had a name, had a mass, had an orbit, everything. So of course all astronomers, they started looking at that, trying to find a new planet, because that is a big discovery if you find a new planet in the solar system. So they started looking at it, and there was various astronomers who said that they observed something. And most of the people were pretty sure that that planet exists. It's just that we cannot observe it because it's so close to the Sun that it's difficult to observe it. So you need better telescopes, you need more time, etc., but one day we will observe it. So there was all these things about this missing planet, and people were trying to find it. But finally, Einstein explained that, is that, and you can find these calculations easily in most of actually the books, is that the theory of gravity is not Newton, so you cannot have just this orbit, which is a simple orbit, but you have some corrections, which are relativistic corrections, which are coming from general relativity. Of course, these corrections always exist for any planet, but for Mercury they are a bit stronger because Mercury is very close to the Sun. So the gravitational effect is a bit stronger. So then you have a bigger effect, but this advance of the perihelion, you get it for any planet actually. So then you do it with Einstein's theory and you get exactly this. So that was more or less one of the first predictions of general relativity, and that was why it became extremely actually important theory, because very fast people understood that we could understand very basic observations thanks to the theory of general relativity. To say a bit more on the numbers, actually you have different effects that people calculated. So let me just put these numbers. The numbers are the following. So first you have the effect from the other planets, as I said. So This is the gravitational tux from the other planets. And you get something which is 531.63 if you do it with a computer, so you have something very precise. The other thing is that the sun is not spherical. It has a bit a shape which is different than a sphere, so that produces also some effect that you can calculate. And these people in the 17th century, in the 19th century, they already did that, but the effect is very small. Then there is the effect by general relativity, which is bringing some correction to that, and you get 42.98. So then you have the total of all this, and the total is telling you that it's 574.64, and what is observed, you get 574.10. Okay. So this is the point where we are nowadays, actually, with this theory. So as you can see, general relativity is pretty good. There are, of course, always some other small effects that you can take into account, etc., to be a bit more precise with that. But it is pretty good in terms of predictions. Okay, so that is the first observation, the first test of general relativity, and this calculation was done by Einstein just following his paper. The second thing, I don't know if you have some comment or question about the first experiment. No. So the second thing is the deflection of light, which is pretty interesting and one of the very important experiments. So let me not erase for the moment and go there. So the deflection of light is also a prediction by Einstein. So we know that the theory of general relativity, what it does is that it produces a deflection, which is that if you have a massive object, so here you have some massive object and you have some light coming, and this light actually will bend like this, will change direction just because of the massive object. Okay, so what is now this angle that you have here, this deviation? So this deviation is, you can calculate it in general relativity, and you get 4gm divided by r0 c squared. This is the radius of the sun, if we consider the sun, of course. And this is the mass of the sun. So this is the sun, and this is the mass of the sun. Okay, so you can get this deviation, of course, if the mass is 0, if you have nothing, it will be a straight line. Otherwise, if you have a mass, more the mass increases and more you get a deviation. So how this actually have been observed, that was a prediction by Einstein before having his theory of general relativity. So that is the very interesting thing. He did this prediction in 1911. And the paper of general relativity is in 1915. Because yesterday we said that he had all this called Gedanken experiment, thought experiments. So just by thinking that you have an elevator, and this elevator actually you can think of it as acceleration is equal to gravity, which is the equivalence principle. And just because of that, he could understand that you have a deviation, and he did the calculations and he found that before really getting general relativity. So this paper is in 1911, 4 years before general relativity. So because of that, since 1911, people were trying actually to observe that. And finally, there was different attempts which didn't work. And the one which worked was in the island of Principe in the west coast of Africa in 1919. So let me say how does it work. Why do we do this observation during an eclipse? The idea is the following, is you observe the sky. So this is the sky that we observe, and let us suppose that there are some stars in the sky like this. So we have the position, we take a picture. This is what he did actually, Eddington. Eddington did that. He took pictures of the sky and he found the position of the stars. Okay, so that is the first picture. Now the point is the following, is that you are here, this is the sun, and this is the earth. And he was looking in that direction, and he could see the stars, which are here. Now the point was, let's wait 6 months. So he waited 6 months, and he was now in this position. So now he is in this position here, 6 months later, and he wants to observe exactly the same stars, except that now the light which is coming from the stars gets deviated from the sun. So now the Earth is not here, so this is 6 months later. And so the light gets deviated. So for us, because we don't see, of course, that light is deviated, we will have the impression that the star is here and that the star is here. So 6 months later, we should not observe that, but we should observe that the stars moved a bit. They have been a bit shifted like this. So they are a bit shifted because of the presence of the sun. The only problem is that if you observe in this direction, what you will see the sun. So it's the day. And during the day, we cannot observe the stars. So the problem is that if you look during the night you observe in this direction. So you don't observe the same stars. So the idea was to say, okay, let's wait an eclipse. If you have an eclipse here, you have the moon. The moon will hide the sun, so we can observe in this direction, so we can see the stars. So this is why this experiment is made during an eclipse of the sun in 1919. So you had to wait that you had an eclipse, etc. And there was a total eclipse in 1919 in this region, west coast of Africa, and you could observe it. So first you take picture in this direction, you get this thing. You wait 6 months, you be here. Now you wait that the moon comes in between, so you can observe exactly the same direction, and you will see that the stars have been a bit shifted in these directions because of the presence of the sun here. So it deviates a bit the light. So he could actually observe that, and he found that there is a deviation. To be completely honest, Eddington was not, he didn't have enough precision. Because if you take actually a photo of a picture of the stars, etc., you don't get a point. You get something which is a bit blurred, etc., because it was not very good quality, of course, of the pictures. So he didn't have enough precision in the sense that he had something more like that. That he had more something like, okay, we can see something, this is a star, and then the second time he could see something like that. So it looks like, yeah, a bit shifted, a bit not, etc. But he was so sure that the theory of general relativity was correct that he a bit kind of, not changed the results, but he said that, yeah, we could prove that, but it was not completely correct. Nowadays, we have very good experiment precision, so now we can be sure. We have just to put everything in context. At that time, there was a lot of tension. We are during the First World War, so there is tension between Germans, French, British, etc. There is the war. And when Einstein came with this new theory, the British, of course, were not happy because it was a German who was coming and tried to say that a British, Newton, was wrong. So it was a lot of nationalism to say that, no, Germany cannot beat England in gravity. Newton is better than Einstein. So actually, Eddington got a grant to do this in order to prove that Einstein is wrong. But Eddington was really sure, he liked it a lot, this theory. And there was no internet, etc., so it was more difficult things because at that time he never heard about Einstein. Einstein published the special relativity since at that time 10 years, but he never heard about Einstein. So people at the Royal Society in UK, they told him that, okay, he has to work on that. He's a good mathematician. So to try to prove that Einstein was wrong. So he started working on it. He got passionate about this theory, and he changed completely his mind, and he tried to prove that the theory was correct. So then he proved that, actually. So that is the second experiment, which is pretty famous. So what is the precision that we have now? The precision is the following, that if you look to, now it's done with actually some telescopes, and what you get is 0.99, there are 4 nines, 2 plus or minus 0.003023 times the prediction by general relativity. And the prediction by general relativity is 1.75 seconds of arc. So this is what we observe actually. It's extremely, I mean, it is the value predicted by general relativity. So again, that proves that general relativity is correct. So if you want to change the theory, if you want to change to go to a modified gravity, that is very easy again if you want to produce an acceleration of the universe. But you have to be consistent with that also. So you have to do the calculations and see that it doesn't actually spoil this prediction. So that is a second prediction, and it's a pretty important and historically also important. It made Einstein actually more famous at that time because he was not known everywhere, and he became famous in UK and in most of the countries in Europe. And then he became actually the famous researcher that we know. The second actually experiment is the gravitational redshift. The third, sorry. Okay. Gravitational redshift is the following, is that imagine that you have the Earth and you send some light in this direction. This light, in order to escape the gravity by the Earth, will lose some energy. So if the energy goes down, means that the wavelength will increase. So actually the wave will get stretched. Something like that. So when this is a prediction also by general relativity, because in Newtonian physics there is no effect at all on light. So this is called the gravitational redshift. So how to observe that? The experiment was pretty interesting. It has been done by Pound and Repka in the 60s. So what they did is the following, is that imagine that they did it in Harvard, actually, on the top of a building. So you have a building, and the building is how tall? Don't have the size, but let's say something like, I think it was like 27 meters, something like that. Okay. So the idea is the following. You have a system here, a quantum system with actually two lines, and you get a disintegration that the transition, sorry, and an electron goes to a lower energy, and it will emit some photon. Okay, so the photon goes down. For example, it goes in all directions, but some of them will go down. And here you have exactly the same system, two lines like this. So if the photon comes here, it has some energy, and if that energy is exactly the same, then here it will get absorbed. So that is if there is no gravitational redshift at all, if the energy doesn't change. So you emit some photon with some energy, the photon goes down here, if there is no change of energy, here the system here is exactly the same. The photon will get absorbed because this is exactly this energy, and the electron will get excited here. So the point is, we know that the energy will change actually. Here, because it falls, the energy will increase. So because the energy will increase, when it arrives here, it will not excite the electron, so it will just pass without any problem. So the idea they had is the following, by Pound and Repka, is to say, okay, let us do something which is this system, we are going to produce a velocity in this direction of this system. At the same time that it will emit some photon, we will move it to, on this direction. And so then you produce a Doppler effect. So you have two effects actually. One is the gravitational redshift, just because of the gravitational field which exists by the Earth. And the other one is the Doppler effect. So actually you produce a velocity in this direction, and when the photon will be emitted, it will have an energy which is a bit less because of the Doppler effect. But at the same time, it will win some energy because of the gravitational redshift. So you can find what is exactly the velocity that you need to produce in order to cancel exactly the gravitational redshift. So this is what I did, in the sense that, okay, you produce some velocity, and that will change the energy of the photon emitted, and it will not be absorbed until you find exactly the velocity that you need in order to compensate the gravitational redshift, and then you get absorption here. So you calculate actually this velocity. And this is what they did. And they found that this is exactly consistent with the theory of general relativity, that because the Doppler effect, we know exactly what is the velocity, and the gravitational redshift we can calculate also. So they found exactly that it works. And now the experiment, what it says, that this gravitational redshift here changes actually the frequency by a value which is 5.13 plus or minus 51, 10 to minus 15. So the change is extremely small, of course, so it's very difficult to observe. But they were very smart enough to imagine this thing about producing a Doppler effect, producing a velocity in such a way that it compensates that. So that is the observation. And that is the prediction by general relativity, which is 4.92 plus or minus 0.51, 10 to minus 15. Okay, so this is another experiment. I don't know if you have questions on this third one. So continuing on the experiments in general relativity, the next one we have is what is called the Shapiro time delay, which is also an interesting experiment. So this is the only effect which has not been predicted at the time of Einstein. When Einstein died, he didn't have any idea of this effect, and it has been predicted only in the 60s actually. So the idea is the following, is that time is a relativistic concept. So if you take the sun and you take some light which comes from any star, for example, and we observe it here. We know that you get some deviation, etc. This we can measure it. Now what's happening is that when it passes through the star, because here you have a massive object, that actually produces, for the observer which is here and an observer which is here, they don't have the same time, because time gets affected by the gravitational field. So we know that gravity affects space and affects time. So actually there is a difference of time between this observer and this observer. So when the light comes here, it passes through a part where the time is not the same. So actually you get a delay compared to what you would have if there was not this object. If this object was not here, you will get it faster. But because there is this object, somehow the time is a bit changed. So because of that, you have this delay. So that is what Shapiro actually predicted. And they measured it, and you get some value. And Poisson. They have only one book together, so which summarizes this kind of aspect. So the idea is the following, is to say that in the weak field limit, because we are always in the weak field limit, means that when the gravitational field is small, that it's almost Newton, but it's not exactly. We know that when it is Newton, the metric is -1, but you get corrections. So it's a series expansion actually, and the metric Gij will be delta Ij 1 plus 2 Gm RC squared plus blah blah blah. So this is just a series expansion in the sense that you say that, let's suppose that there is no mass, so G00 is just -1, and here also you get just 1, so this is just Minkowski, but then you have a perturbation around Minkowski because there is some mass now which produces some effect, and this you can do it by a series expansion. This is a prediction by general relativity. So general relativity is telling us that we have this. The other theories of gravity, they say, no, it's not exactly this. We get actually some parameters, beta and gamma. So the other theories of gravity, they introduce actually when you do this expansion and you solve it, you get two parameters. Of course, we understand that general relativity says that beta is equal to gamma is equal to 1. And if you look to any theory of gravity, which is not general relativity, it will predict something which is not 1. So then it's very interesting to calculate these parameters because it's a direct test of general relativity. So people do that by looking to the planetary positions at different moments and see how they move actually. So you can from that trace back to the parameters beta and gamma. And what do we get from the observations again is that beta is 0.999 plus or minus, and gamma is 1 plus 2.1. Okay, so this is what we get actually. So again, we are at something extremely close to general relativity. So everything is in the range of, this is 2 sigma, in the range of 2 sigma consistent. We will see this afternoon what is sigma 1, sigma 2, sigma, etc. It is again consistent with the theory of general relativity. So again, it proves that the theory of Einstein works perfectly well. What is PPM? Yeah, it's post-Newtonian formalism actually. So it's just a formalism which says that we are doing a series expansion. So this is what you will get in the book by Wheeler and Poisson actually.
And this is 0.999 you are writing, right?
Yes.
Point, that is?
Yes.
Point. Yeah.
Yeah, depending on countries.
Okay.
For me, a comma is.
Okay.
Yes.
Okay, just I have one question. That,
Yeah.
it is interesting that in the Shapiro time delay, means your time would be delay. Time delay would be there near sun of the observer for that observer. But will it affect this observer on near Earth, or she is very far from the sun? Is there any effect of that effect of time delay?
On Earth,
Yeah.
there is always an effect as soon as we have some curvature of space-time. But if it is large enough, I don't think so. It will be extremely small, because already just for the sun, I mean, it's a quite small effect. So for something like the Earth, it will be extremely negligible. If it is observed, no. No.
So
On
this
Earth, no.
delta T, it is you have written for this sun, nearby sun only, no? That if there is a sun, this would be the difference.
Yes.
And if there is no sun, it would be like this. That is the delta T, no?
Exactly. So the experiment is made in this way. So you have the Earth, which is here, and then you have some spaceship that we send somewhere, and this will send us some signal to us. So we know when it left, we know when it arrives on Earth, so we can measure the time. And we wait for the sun to move. And at the beginning, when the sun is here, we have some time. And then when the sun starts coming closer, we'll see that that time changes. So when the sun is exactly here, this is where you have this time delay, which is much larger actually. And then it passes, and then again the time delay decreases. So this is how actually they observe it. So they did this experiment, and you see something which is doing like this, and then it decreases. So this is the time delay. At the beginning, when the sun is far enough, you observe nothing, and when it is just like here, you observe a maximum in this time delay. Yes, so let me continue on some other interesting experiments. One is called the Lunar Laser Range Experiment, LLR. And this is something which is used actually to measure the distance to the moon, because we can ask, how do we know the distance to the moon? This is the mission Apollo, I forgot, I think 8 or 9 or something like that. When they went on the moon, what they did is the following. So let me maybe erase this part. So it's called the LLR experiment. Why is it an R now? Ah, yes. Okay, so the experiment is the following, is that on the moon, you put actually here some mirror, and that was put there in the 60s or 70s during the mission Apollo actually. And us, we are here on the Earth, and what we do is that we send a signal here with a laser, and it goes there, bounces, and comes back. It goes and it comes back. So we know that it goes with the speed of light. We measure the time it takes, so then we can measure the distance to the moon actually. So we do that since the 60s. Now it's more or less like 50 years that we do this experiment. So we know very well the distance to the moon actually. So you send a signal, it goes there, bounces back, and comes back. Actually, we do that with other planets. But on the other planets, it's called an echo, actually. On the other planets, we don't have anything there to bounce it very well, so it just gets reflected by the surface of the planet. So then you get some dispersion, it's not very good, you don't get a good signal which comes back. But on the moon, because we have this, you get a really good actually reflection, so it comes back, you measure the time it takes, you know the speed is the speed of light, so you get the distance. Of course, what we observe is that the distance between the moon and the Earth changes over the year. So during winter, the distance is not the same. During summer, etc., not winter, summer, but during the year, the distance is a bit closer or not. So that changes. But what we expect is the following, is to measure something which is called the equivalence principle. So the equivalence principle is also a very important in the foundations, actually, of the theory by Einstein. So the idea is the following, is that imagine, because sometimes when I say that the Earth and the Moon, both of them actually are falling towards the Sun, people, they look at me strangely, but let me explain it in this way. Both of them are free falling. Let's suppose that this is the Earth. And let me take an object here and just throw it. It will go and fall back. So we know that, we studied that in Newtonian mechanics, it has a parabolic trajectory. Now let us say that I'm going to send it with a bit more energy. It will do like this and falls back again. So now if I throw it with a lot of energy, a bit more, it will do like this and maybe falls here. If I put enough energy, it will do this, and then it gets an orbit. So what is an orbit? Is an object actually which is always falling. So the object goes, it falls, but because the Earth is round, so it takes a bit more to fall. If it goes like this, because the Earth has this curvature like this, it falls back actually to the Earth. It's just that there is no ground anymore, so it continues falling. So here it falls again and again and again, but it falls all the time. It's just that there is no ground anymore, so there is no Earth, so it continues falling. So you can see that an orbit is just a free fall. So this is how you can understand it. So if you look to the orbit of the Earth and the Moon around the Sun, you can understand that the Earth and the Moon are falling toward the Sun, actually. And the equivalence principle here, the strong equivalence principle, what it says is that the Earth and the Moon have different masses. So if the equivalence principle was violated, they should not fall with the same acceleration. So, for example, the Earth will fall faster. If the Earth falls faster toward the Sun, then the distance between the Earth and the Sun will, between the Earth and the Moon will increase, because the Earth will fall faster than the Moon. So that is the idea of measuring the distance between Earth and Moon. So as I said, during the year, actually this distance changes, but if you average it during 1 year, you should get always the same distance. So since 50 years, people are measuring that, and since 50 years, they haven't observed any variation of the average distance between the Moon and the Earth. So which means that they are falling really with the same acceleration. So the equivalence principle works pretty well. I will say a bit more about that because there was an experiment published just 1 month ago when we will talk about F of R theories, the chameleon mechanism, that it's called microscope, and it says something about this modified gravity theory, and it is pretty actually interesting. So measuring that, this distance, you can actually shift it to the acceleration to the Moon minus the acceleration to the Earth divided by the acceleration of the Moon plus the acceleration of the Earth. So if the equivalence principle is exactly verified, we should have this equal to 0, but we don't have the experiments where they say is that this is less than 10 to minus 13. So with a very, very good accuracy, we have that this is that the strong equivalence principle is not violated. So acceleration of the Moon, and this is the acceleration of the Earth. Okay, so this you do it with this lunar laser range experiment. At the same time, you can shift that by the change of the gravitational constant. Imagine that in general relativity, the gravitational constant is constant. It's equal to 6.67, 10 to minus 11, and the units, so the Newtonian constant. But in theories of modified gravity, very often this constant is not a constant. It changes over the time or the space. So you get, for example, that G depends on time. So gravity has not been always the same. In the past and today, gravity has changed. And there are many theories which predict that. So actually this experiment, because we do it since 50 years, if gravity changes, you will get actually a constraint on G. So people could actually write this experiment in terms of the variation of G, and they found that it is less than 9, 10 to minus 19 per year. So that is again another experiment which is showing that if if G is changing over the years, it changes very little. So again, it shows that general relativity is a very good theory. So we'll continue on that, but what I'm trying really to explain that it's not easy to change the theory of Einstein. You have to keep in mind all these experiments. Each of them is important. Each of them is saying that GR is the right theory. Another experiment which is made in laboratory is the following. So you will have all of the things in my notes actually. I'm trying mostly to explain what's happening. One experiment which is made in a lab is that we know that the gravitational potential, according to Newton, is minus G m1 m2, a first mass times a second mass divided by r. Let us suppose that we don't have this, but we get some correction, I call it lambda. That we have something like that. So that the Newtonian potential is not exactly this, but you get some deviation. And many theories of gravity, they produce something like that. So you don't have exactly Newton. So in this case, what it says, what the experiments are saying, these are known as the Edvosh experiment. You can look online to Edvosh is this. There is the Edvosh group in Washington, who is, as far as I know, the only lab actually doing this experiment. One of the only labs, but they publish every 2 years, 3 years, their new constraints on this parameter alpha and lambda. So according to general relativity, in the weak field limit, we should get Newton. So Newton is this. It says that between two masses, m1 and m2, we have this gravitational potential. In some theories, you get some deviation. So GR would say that alpha is 0, and that's it. So what are the experiments? They say this thing. They say that the constraints on alpha and lambda, so if I call this 10 to 4, 10 to 3, this will be 1, this will be 10 to minus 6, 10 to minus 5, 10 to minus 3, 10 to minus 2, and what you get is this region is excluded. Okay, so what it says is the following. Imagine that you don't have only the Newtonian potential, but an additional force in some sense. We call it very often a fifth force. What's happening is the following, is that if the range of the force, because lambda is the range of the force, so if you go to 1 meter and lambda is 1 meter, so you get just an exponential minus 1. So lambda is how far the force can go. So this is the range of the force. So if you want actually some parameter alpha, which is of the order 1, means that you want a theory which you don't fine-tune too much. So what you need is lambda, which is, it's not exactly this. It is 10 to minus 4. So you need actually, if lambda is of the order 1, you need lambda, alpha is of the order 1, lambda has to be less than 10 to minus 4. What does it mean? It means that if you have a theory where this parameter is 1, and you go at a scale of the order 10 to minus 4 meters, the Newtonian potential will be correct. If you take two masses and you put them very close to a distance of 10 to minus 4, Newtonian physics works perfectly well. If you want to observe something, you will have to go to much smaller, actually, distance between them, but then it becomes very difficult to test. So every time they publish a new thing, and every time they are taking a bit more, actually, here. Every year they increase a bit that. So you would say that, no, actually, I don't want that. I want some experiment which is producing some effect which has a range of 1 meter, but if you want 1 meter, you need an alpha which is extremely small, so something of the order 10 to minus 6. Then you will have to start explaining why alpha is so small. So then there is some sort of fine-tuning, why these parameters, they take very small values. In physics, when you have a dimensionless quantity, you always want it to be of the order 1, which is more natural in some sense. So that's actually, it's excluding a lot of theories, actually. This is a very, very important experiment in modified gravity. Gravitational waves have been discovered, as you all know, in 2015. Most exactly, we should say direct observation. There is a philosophical debate if it is direct, if the first one was indirect or direct or not, because you know that there was a first observation in '74 by Taylor and Hulse on the binary system. The idea was the following. The experiment is the following, was that you have a binary system, you have two stars, the star 1 and star 2, and actually they have their motion like this. So you have a binary system, but at the same time what is happening is that they emit gravitational waves, and because they emit gravitational waves, this binary system, just by one thing is that in gravity there is a theorem which is called Birkhoff theorem, which tells us that if you take a spherical object, like if the sun is perfectly spherical, it will not emit gravitational waves. If you want to emit gravitational waves, you have to deform it, or you have to take two objects like that, because in this case it's not spherical. So you need really to have something which is not spherical. So here, for this type of object, you have two objects, so it doesn't have spherical symmetry. So then you produce gravitational waves. And the gravitational waves makes that these two stars are losing some energy. The system is going to lose energy. Because it loses energy, they come a bit closer. So they change a bit their orbit. So they come closer and closer. So because of that, the periodicity of the system is going to change. So first they have some periodicity, and that periodicity will actually increase because they come just much closer. So this, you can do the calculations. There is a good book which is called Gravitational Waves, where you will find the full calculation. This is, as far as I know, maybe the only book really about all calculations in gravitational waves. And it's a pretty interesting, actually, book. And so you do these calculations, and what you find is that the periodicity changes over time, and you get something (997) plus or minus 0.002 times the prediction by general relativity. So this is the orbital decay by general relativity, the prediction, and this is what is observed. So again, as you can see, it's very consistent with general relativity. So that is what we call, that is done in 1974. And this was observed in 1974. So since 1974, we knew that gravitational waves exist because we measure it. We measure, but indirectly, some effect that the gravitational waves that are emitted, we don't observe them directly, but they have an effect on the periodicity of the stars because the system is losing energy, so they come closer, so the periodicity is changing. But it's not a direct observation. The one here, they call it direct, but we can say again that we don't observe it directly because it goes over an interferometer, and what you observe is the interferometer. You don't observe directly gravitational waves. So maybe we should call it also indirect observation. There is no direct observation usually in physics. You always observe things through something else. But more or less the idea is here, the gravitational waves doesn't come to the Earth. In the other case, it comes to the Earth, so we observe it at least on some device here on Earth. So that is the difference. But the discussion about direct, indirect is... yeah, it's not that clear. So that was the first experiment. Then came LIGO. We will talk a bit more on theory of perturbations for black holes on Friday. So I'm not going too much into details now, but that says also that there is, it's consistent with general relativity, definitively. I will say a few things later on about it. Okay, so what it says, what is the conclusion of all this? First of all, we saw few experiments. There are much more, and on Saturday we will see few more when we will see modified gravity theories, and we'll try to see if the new theories are compatible or not, because there have been a lot of experiments, principally on the theories that I will talk about tomorrow, how to prove if they are correct or not. And there was a lot of literature on that, a lot of experiments in the lab to try to see that. Now the thing is, so far what we have seen is that the theory of Einstein is extremely compatible. So in some sense, why should we change it? But at the same time, all these experiments, as you can see, they are done at small scales. They are done in the lab, they are done in the solar system, they are done around the binary system, a black hole. Everything is at small scales. When you go at much larger scales, you start getting the other problems that we talked about, the dark energy problem, why the universe is accelerating. That GR cannot explain it easily, or it can with a cosmological constant, but comes some other problems. There is the problem of inflation, which is also at large scales. There is the dark matter problem, which I didn't talk about, but which is another problem. So it seems to be that what we have is the following, is that at very, very large scales, maybe GR doesn't work very well. So that would be nice to change GR at large scales. But at small scales, where we do all these experiments, GR is perfect. So if we want to build a theory, that will be the philosophy, is to modify the theory at large scales, but at small scales we should recover GR. That is the fundamental thing. If we don't recover GR, the theory doesn't work because it has to be consistent with all this. So then comes how to modify GR. There is a theorem by Lovelock which says an interesting thing on how to change the theory. If we want to change it, to explain the things at large scales. If we want to change the theory, there is a theorem by Lovelock which says the following. That you need 4 conditions. The first condition, you need a theory invariant and a diffeomorphism. The second assumption, that you consider that the space-time has 4 dimensions. The third condition is that the metric is the only field that you have. And the fourth condition, is that the equation of motion is second order. If you have these four conditions, the only theory is general relativity. Okay, so that is what the theorem says, that what is general relativity? It's an equation of motion. We saw it yesterday, r mu nu minus 1/2 r g mu nu equal to 8 pi g c4 t mu nu. And this is a differential equation, which is second order differential equation. So we have this. The metric is the only field here in the curvature. There is no scalar field or something else. So this is the only field that we have for curvature. We are working for dimensions, definitively. And this is a theory which has this symmetry, the change of coordinates. So it's invariant under diffeomorphism. And you can prove that this is the only theory which you have. Now, if you want to modify gravity, you will have to violate one of these four conditions. So this is how you modify gravity. If you want to do it clearly, you have to modify one of them. So some people, they go to extra dimensions. They say the universe doesn't have 4 dimensions, but 5, 6, 10 as string theory. Then you get something which is not GR. It's something else. You can say that the metric is not the only field, that maybe you have some additional field, like a scalar field. We talked about it yesterday, and I will continue that tomorrow. So you say that maybe there are some other things. Here, the equation of motion is not second order. Maybe you can have an equation of motion which is fourth order, etc. And there are these theories like f of r gravity. It's a bit more tricky to have a theory which is not second order differential equation for many reasons. One of them is just to get the nice limit. We know that in some limit we should recover Newton, and Newton is the Poisson equation. So the Poisson equation is a second, this is the Laplacian, and this is a second order differential equation. So in some limit we should recover that. We know that Newton is a second order differential equation. Newton is the summation of forces is equal to the mass times the acceleration, and the acceleration is a second derivative. So it's a second order differential equation. General relativity is a second order differential equation. It's maybe not a coincidence. There is all this thing known as the Ostrogradsky ghost, etc. I'm not going to talk about it. If you want, we can talk about it later. But that maybe we should consider only a second order differential equation when we describe gravity, because otherwise we might enter into troubles. And this one is a symmetry. And if you violate that, there are some theories which are called massive gravity. And if you violate that, and you get a new theory again. So you have 4 different directions. And actually, you can prove that in many ways, things are a bit equivalent in some way, that it's equivalent to other scalar field, but I'm not going into these details. So we...
What does, the first one, what does mean invariant under deconformity?
Diffeomorphism. This is the change of, if I have a coordinate system x mu, and I change it to any coordinate system x prime mu, which is any function of x. We know that special relativity is invariant under some very specific transformations, which are Lorentz transformations. Only that. So you will have that ct prime is ct minus x, something like that, and also on x prime. So you have just the Lorentz transformation, the boost, and etc. But in general relativity, this is what you generalize actually. It's invariant under any transformation. So physically means that any observer will see the same physics, because when you change this thing, you are talking about another observer. So we have an observer, we can observe some physics. Now you go to another observer, you do this transformation. This other observer should see the same physics. So physics should not depend on the observer which is looking at it. So this is what it says.
In FR theory, basic
Yes.
field which remain, you can G mu nu.
Yes.
So what is the problem actually? It's satisfying?
No, it doesn't satisfy this.
Is it ghost problem?
No, it doesn't have a ghost problem. This is the unique theory, which this is why it's very popular. So f of r, sorry, so just for the others, f of r is so I will say the first lecture tomorrow morning will be on F of R, but just to say what it is that if you consider an action, this is the action of general relativity, and we saw yesterday that there is this proposal by Starobinsky 30 years ago to consider something like that, like a correction. But then you can change it and you say, yeah, why not considering any function of R, any function of the curvature? So these theories are called F of R. This theory gives an equation of motion which is fourth order. It's a fourth order differential equation. But the interesting thing is that this is the only theory of this way which doesn't have this Ostrogradsky ghost. I have some notes about that I wrote because I did some lectures in Benin, and I was talking about the Ostrogradsky ghost, but I don't think I have it here. It's equivalent to other scalar field. Also this, it's called massive gravity. Massive gravity in some limit, which is called the decoupling limit, you get something which is called the Galilean field. So in many of these theories, in some limit, you get a scalar field. Okay. So we will add a scalar field. And what we want is that this scalar field, we should hide it completely at small scales. It should not exist. So we should find a mechanism to screen it completely. Then that scalar field doesn't exist for us. If we do an experiment in a lab in a solar system, we don't observe it. And but at large scales, that scalar field will start having playing some game and try to produce an acceleration of the universe. So for that, we need something called a screening mechanism. That at very, very large scales, the scalar field plays some game, does something, but at small scales, that scalar field is hidden and we don't see it anymore. So that will be the logic, and there are mostly two mechanisms, which are called the chameleon mechanism and the Weinstein mechanism, which appear, many people, they work with it, but they don't necessarily know it. The F of R has the chameleon mechanism, the massive gravity has the Weinstein mechanism, etc. Most of the theories which are popular in literature, they have this mechanism. If they don't have this mechanism, they will not pass at all these experiments. So that's the logic. At small scales, we have to hide everything. We just have GR. At large scales, we don't have much of constraints, and we want to explain acceleration of the universe itself. So that is the logic. I don't know if you have questions so far. Yes?
Yeah. So what you are mentioning is that means at local level means in our solar system and little bit far of it, GR is okay.
Yes.
Okay, but at larger we have to modify it in some these alternatives are there.
Mm-hmm.
But on another way, if we go backward, that in the early universe also GR is not that much perfect. You
Yes,
see,
yes.
near space means in black hole or near Big Bang.
Yes.
At that time also we need some.
Yes, yes. Yeah, there are two directions.
Yeah.
One is when I'm saying here nowadays at large scales, is at very low energy actually, because if I go at if I'm close to a black hole, energies can be large, but if I go at very, very large scales, there is very little of matter in the universe finally, and I'm at very low scale, low energy.
No.
So this is a modification of GR, which is called infrared modification. So this is what I will mostly talk about. The other one is a modification at very high energies.
Yeah.
And so in the very early universe, for example, to solve the Big Bang problem, the singularity or near a black hole, etc., this is the UV, modified gravity. So you have two types of modification. Either you modify it at very low energy or you modify it at very high energy. One thing is sure is this one. This we have to do it for sure, because we know that GR doesn't work at high energies, because we need a quantum theory of gravity.
Yeah.
But at low energy, it's not that simple, because we have problems with large scales, but is it really true that we have problems or not? It's debatable, because there are these problems of dark matter, dark energy, etc., but it's not very clear if there are really problems. Some people consider that there are not really problems. We can add, as I was saying yesterday, some exotic matter Dark matter is this. There are mostly particles which are produced in some theories which are called supersymmetry. So we have a lot of candidates for that. Even if now at CERN in Geneva, where they test particle physics, and so far they haven't observed supersymmetry, so they haven't observed any other particles. So what we see is really what we have in the universe so far. There is nothing else. So we are really at a point in physics where it's a bit tough, because many theories which predicted a lot of things like supersymmetry, a lot of particles. So the Higgs boson has been discovered. This is the last discovery. Since, nothing. So now it's quite few years. The Higgs was in 2012. So it's now 5 years, and not much actually has been discovered. So people are expecting this supersymmetry, but nothing. So if there is no supersymmetry, dark matter has to be explained in another way. Dark energy is another problem, is much tougher actually. Everyone who tried failed in some way. There is no correct answer actually. I would have to take a full lecture to explain the dark energy problem. But yeah, it's debatable. Some people they say no, we just keep the theory like that, GR works, and at large scales we just add some exotic things and that's fine. But we don't observe these exotic things, so that's the difficulty. So there are two paths, either to change GR or to add exotic matter. Both are correct, and experiments will in the future decide. But I will talk about experiments mostly on Saturday to finish about gravitational waves, what they say on these modified gravity theories. For example, the speed of light, the speed of gravitational waves. There are many theories which are saying that the gravitational waves, they don't propagate at the speed of light, but now we know that it should. So we have many more experiments which are putting constraints actually on the theories of gravity. So it becomes actually more and more difficult to change Einstein. More and more we have constraints, more and more we have less freedom actually. In the past, when I started my PhD, there was a lot of freedom. We could do whatever we wanted. You write an action, a Lagrangian, you write some equations, and that's it. Now it's a bit more complicated. Yes?
As you mentioned in the case of gravitational redshift, like when energy, like when it goes up, so there is a gravitational pull, so what it does, the energy of that particle or wave, it decreases. So we say it a gravitational redshift because the lambda will increase. But if we do the experiment in the opposite direction, like energy coming from the up to the
blue shift
towards Earth, so will it be like a blue shift after
yes.
that?
Yes, it's a blue shift. Yes, this is what I was saying about if you take this building and the photon goes down, then it's blue shifted actually.
So why it is specified as a gravitational redshift?
That is historical reasons. So they thought of it in this way, that when you have to escape from an object, you lose energy, so you call it redshift. But of course you have blue shift also when you fall into it. But it's just, yeah, they kept it like that. But yeah, it might be a bit confusing, but you get blue shift also, yes. Yes.
There is a difference between cosmological redshift and gravitational?
In some way, no, because both are produced by gravity. One is produced directly by the Newtonian potential. The other one is produced by the expansion of the universe. But both are produced by the metric at the end of the day, actually. So in that sense, they have the same origin. But in terms of metric, it's different. One is like Schwarzschild solution. So you have this G, M, etc. The other one is expansion, which is Friedmann universe, which is at scale factor. But both are produced by metric. If the metric is flat, if it is Minkowski, of course, we don't have anything.